Hello everyone. In this session, we'll be discussing about viscosity and a characteristic. It is a characteristic property of fluids. Other properties like density and then unit weight or specific weight, cohesion and adhesion. You can talk about other materials, but for fluids, viscosity is a characteristic property. It is there only for fluids. It's not there for uh, solids. So we'll discuss this. We'll go to the next slide. Before going further, we'll revise a little fundamentals. So we should know these basics. When an object is moving with resultant force acting on it as zero, then the velocity of the motion must be. Think of an answer. I'll try to explain the same thing, but if you can come up with an answer, it will be better. You have an object, it is said that it is already moving, and the force on this is equal to zero. There may be vertical force, horizontal force, inclined force, all those forces are equal to zero. So you can write that it is sigma F is equal to 0. Then what? Then the velocity of the motion must be what it should be. If it is v, then so here we should recall that it is F or sigma F, resultant force is equal to m into a. We know this second law of Newton's. So when this is equal to 0, when there is a body existing, it will be having a non-zero mass. So only what we can conclude here is acceleration must be equal to 0. If acceleration is 0, then what should happen to v? Therefore, v is a constant. So if it is a constant, then it is a uniform motion. That's what we can say. So here it is a constant velocity motion, or it is a uniform motion. Uniform in the sense without any acceleration, it just goes on with the same velocity. So when this is possible when the resultant force on the object is 0. So that is what is the first problem one should understand, because while discussing we'll be taking a lot of cases where the resultant force is 0 or constant velocity. Okay, the second situation, if an object is in equilibrium under the action of forces F1 and F2, then F1 and F2 must be dash in magnitude and dash in direction. It is quite simple. If you have two forces and they are in equilibrium, obviously how they should be, one should be going this way, and then effect of that has to be perfectly nullified. So if you have F1 this way, the F2 should be in the opposite direction, but it should have the same magnitude. So answer for this is they must be collinear. Collinear in the sense they should be acting in the same line, but opposite in direction. Must be dash in magnitude. Oh, dash in magnitude is equal in magnitude. What I can write is equal in magnitude and opposite in direction. So opposite direction. That is the second statement. Third one, if the shear stress is 5 Newton per millimeter square, shear stress is generally represented by the letter tau, a Greek letter. It is given to be 5 newtons per millimeter square is acting on an area of 10 centimeter square. Then the shear stress is, so here it is in millimeter square, here it is in centimeter square. You cannot just multiply, because you know that stress is given by the force divided by area. This you know. Now area is given in units of centimeter square and having a magnitude of 10, and stress is 5 newtons per millimeter square. So when you multiply, there will be a mismatch of millimeter square and centimeter square. So you have to take care of this situation. Always this happens in fluid mechanics. Now and then there will be variety of units are considered, so one has to be very careful. So if I want F, this is 5 Newton per millimeter square. You convert 10 centimeter square into millimeter square, or you convert this into 5 Newton, so many newtons per centimeter square. Now it is easy to convert this. How do you do that? So every centimeter is a 10 millimeter. Because of that, here I can substitute 10 millimeter into 10 millimeters. So it becomes 10 into 10, 100. So 10 multiplied by 100. That will be 1000 millimeter square. 10 centimeter square becomes 1000 millimeter square. Okay. So 1000 millimeter square multiplied by 5 newtons per millimeter square. The millimeter square cancels off with this millimeter square. You will be left with 5 into 1000, that is 5000 newtons. So 5000 newtons can be written as 5 kilonewtons, and that would be the answer. You can write as well 5000 newtons also, but it is better to use a smaller number. Okay, then the last one, cylindrical surface area of a radius 7 centimeter but of length 10 centimeter square. So you have a cylinder of length 10 centimeter square and then radius. So radius is 7 centimeters. So in this case, I think everyone knows. So how to calculate cylindrical surface area? Means the area which is bent like that, not circle areas. What we are interested in is cylindrical surface area of radius. So what we have to do is you have to cut this into a plain sheet like that. The height of the rectangle remains the same as 10 centimeter. I'm able to write properly. Anyway, this height remains as it is. When you make a cut here, it gets opened into a form of rectangle, and this periphery, that is circular periphery, becomes a length like that. And if r is the radius, then this becomes 2 pi r. That would be the length over here and over here also. So 2 pi into 7, that is 14 pi would be the, in this case 14 pi would be the length. Width is 10. So because of that, area becomes 14 pi into 10, that is 140 pi, and units become centimeter and centimeter we are multiplying. So it becomes 14 pi If you substitute the magnitude of pi, you'll be getting whatever product comes. And the units is centimeter square. That's an important thing. So that's how we can calculate cylindrical surface area. If you want the formula will be 2 pi r h. If you hold this height as h, then it will become 2 pi r h would be the cylindrical surface area. So these are the 4 points one should know thoroughly. Remember them so that further discussion or understanding becomes simple. I will go to the next slide. Okay, here viscosity is the property of fluids offering a resistance to the motion of one layer to the other layer. Okay, this is resistance for the motion in fluids. But if you take a resistance of motion in solids, suppose there is an object here, it is shown, a box sitting on some surface. When you try to push this, direction of motion or attempted motion means it is being pulled, then what happens is there will be, this box will be having a tendency to move in this direction with respect to the surface. Obviously, naturally, the surfaces will not be perfectly smooth. There will be some kind of roughness. It is exaggerated and shown over here. And because of that, there will be a resistance. And that resistive force is friction. So whenever two solids are in contact and one solid is being moved with respect to the other, obviously there will be a resistance force, and that we call it as friction in case of solids. But in case of fluids, suppose there is a fluid over here, right? It is showed in layered so that you can imagine. Otherwise, there won't be any distinct layers as such because it is all molecules. Okay, you can imagine a layer of molecules there, and second layer of molecules, next layer of molecules, and so on. Now here also, the top surface, there is some plate, let us say, and this is being pushed. So when you push it, the liquid beneath that may not be readily coming. So it offers resistance, and that resistance in the fluid we call it as viscous force, and the property which offers a resistance of motion in fluid is named as viscosity. So the resistive force at the bottom of the plate because of viscosity is Fv, force because of viscosity, Fv, viscous force, known as viscous force. Now the shear stress because of viscous force is represented by Greek letter tau. Means when there is a force over an area, obviously there will be intensity of the force, we call it as stress, and the shear stress because of this resistance whatever is produced, it is represented by the letter tau. So tau, the shear stress because of viscosity or viscous stress, is equal to viscous force divided by the area in contact. Okay, we'll go to the next slide. Here a lot of things are written. So the picture that shows is top plate moving at a velocity of v, right, under the application of force F. The area of the plate is A, and here there is, at the bottom there is a stationary plate, and in between there is filling of fluid, and the thickness of the fluid is shown as T. This is stationary, this is not moving, but this is being moved with a constant velocity. So we shall assume a constant velocity of motion. So when it is being pushed and maintained with constant velocity, what happens is there will be, as discussed, a resistance, and then on the plate there will be a resistance, and then once this layer is being moved, obviously there will be a resistance there also, and when this is moving with respect to the lower layer, again there will be a resistance. So like that, between the layers of the liquid there will be resistance, right? Okay, we'll try to analyze this. Velocity is constant, you know that acceleration is zero. Because of that, F equal to ma equal to 0, and we know that acceleration is 0 in the sense velocity is 0. Because of that, it has to be equal to 0. But what is happening is there is a resultant force, and here there there has to be a frictional force of resistance. So here there will be a resistive frictional force Fv, and because sigma f is equal to 0, F rightwards minus leftwards is equal to 0, hence Fv equal to F, right? So applied force on plate is equal to viscous force, and viscous force is equal to tau into A. Because of that, we can calculate tau, the shear stress. Fv by A would be the shear stress. So here, if you look at the lower sketch, the velocity of the plate is u or v, whatever it is shown here. On the upper diagram I have shown it as v, so it can be put as v, and as you go below, the velocity becomes less and less, and ultimately there is a stationary plate. What is the rate of change of velocity? If we ask, it is v divided by t. But if you take very elemental strip and then thickness y, because in this direction it is y, so gradient or the rate of change will be equal to dou u by dou y in thickness t. So dou u by dou y is nothing but velocity gradient, rate of change of velocity, and it can be put as this u or v divided by t. Because it is a linear variation, it can be put as simply u by t. If it is non-linear variation, it is obvious that you have to take uh, differential form du by dy. Now, du by dy is also known as the rate of strain, because if you look at this figure, when you apply a force, it is getting tilted. Means, if I try to draw over here, an object when it is erect like that, when you apply a tangential force, it tries to uh, bend in this manner. That is what is happening because of the applied force. So there is a strain. So the rate of strain is u by t, right? Also known as rate of strain. Now, where t is the thickness of the fluid, here also and then here also it is clearly shown. Now there is a law of viscosity defined by Newton, and it is like this: Newton's law of viscosity. The shear stress, whatever tau we have, is directly proportional to the velocity gradient. So if I put it in the equation form, it's quite simple. The shear stress tau is directly proportional to du by dy. Now if I want to put it as an equation form rather than proportional equation, introducing a constant of proportionality, tau will be written as mu into du by dy, where mu is a proportionality constant, and it is known as dynamic coefficient of viscosity, or just coefficient of viscosity, mu. Okay, the next slide. Now we know that tau is shear stress measured in Newton per millimeter square, because Newton per millimeter square or Newton per meter square, anyway, Newton the force divided by area, that is what should be the units of shear stress, or it can be also put as simply pascals, because 1 Newton divided by 1 meter square is 1 pascal. That's a unit of stress. Now du by dy, the velocity gradient, may be equal to u by t, is measured in what units? U is measured in meter per second divided by what we have is t. The t is nothing but thickness of the fluid, so it is measured in meters. So overall units will be 1 by yes, that is 1 by second. That is, we call it as per second. So how it is read is, this particular part is read as per second. Okay, the shear stress is in pascals, and then shear strain or velocity gradient is in terms of per second, and we know that tau is equal to mu into du by dy. So we can write mu as tau divided by du by dy. Now we'll try to evaluate what would be the units of mu. Now hence, units of measurement of dynamic viscosity will be uh, Pascal, that is tau shear stress, divided by du by dy is per second. So if you simplify this, it will be quite simple. Pascal second we call it as, or Pascal is Newton per meter square. If I substitute, it will be Newton second per meter square, right? So the units of measurement of dynamic viscosity will be Pascal second or Newton second per meter square. We know 1 Newton is nothing but 1 kg per meter square because of F equal to ma. Everyone knows, right? If we try to analyze even that, here F equal to m into a, and if I substitute 1 Newton force, and that is applied on 1 kg of mass, then what happens is 1 Newton is such a force that it will be producing acceleration on 1 kg mass as 1 meter per second squared. So we can always substitute as Newton equal to kg meter per second squared. So one can remember this. A Newton force or 1 Newton force is sufficient to develop an acceleration of 1 meter per second squared on a body of mass 1 kg. Because of that, Newton is equal to kg meter per second squared. Okay, hence Pascal second is equal to, if I substitute this over here and simplify, I'll be getting kg per meter second. Even this can be unit of dynamic viscosity. Generally it is in this form, Pascal second. Once you know what is Newton, etc., you can deduce readily what would be the units, and try to remember this expression also, kg per meter second. Hence the dimensions of mu will be, kg is mass m divided by lt, meter and second, so length in time units. So m by lt, or m into l raised to minus 1 t raised to minus 1 would be the dimension of dynamic viscosity. Now, the ratio of dynamic viscosity to the density is known as, there is one more way of representing viscosity, it is called kinematic viscosity. So, what it is kinematic viscosity? It is simply a ratio of dynamic viscosity mu and the density rho. And this kinematic viscosity is represented by a letter nu. It looks like a lowercase letter v, but it is a Greek letter nu. So nu is equal to mu divided by rho. Hence, units of measurements of kinematic viscosity will be, you know that this is Pascal second, this is kg per meter cube. So this is kg per meter second, this is kg per meter cube. If you simplify, we'll be getting kinematic viscosity as, units for kinematic viscosity as meter square per second. So from this slide, what we can conclude is there are two viscosities, dynamic viscosity and kinematic viscosity. Units of measurement of dynamic viscosity are Pascal second or kg per meter second. Units of measurement of kinematic viscosity will be meter square per second. It can be uh, converted to centimeter squares per second or millimeter square per second. That can always be done. Okay, we'll go to the next slide. Some more units of measurement of viscosity. Now, for convenience of their magnitude, because viscosity is a very small force, because of that, if we apply the earlier units, what I mean is meter square per second, it will be a very unit will be, the magnitude of the unit will be very small. So because of that, we adopt some other units. Now here, for poise is the unit for dynamic viscosity, and Stoke would be the unit for kinematic viscosity. Now, how much it is? So 10 pies will be making 1 Pascal second. 10 pies is equal to 1 Pascal second. That's how it is defined. Poise is also a name of a scientist behind that. Stoke is also a name of a person. Because of that, whenever we write full length um, unit, it has to be a lowercase letter of p, and then here also there is a mistake. It is Stoke is a lowercase letter Stoke. So I'll correct that. It is a smaller case letter. It should have been. Anyway, 10 poise is equal to 1 Pascal second. 10, if you want still smaller units, so what is done is 1 poise is broken into 100. So 1/100th of a poise will be known as a centipoise. 1 centipoise is equal to 1/100, or 100 centipoise is equal to 1 poise. I think it is better remember that way. That is 1 centipoise. 1 centipoise will be equal to 1/100th of a poise. 1/100 of a poise. And that will be fine. Centipoise is equal to 100th part of a poise. Okay, here in the next line, what is shown is a Stoke. So Stoke is nothing but centimeter square per second. Means 1 centimeter square per second is named as Stoke. So we have 1 meter square per second. If we have, then 1 meter is 100 centimeters. So if I calculate 100 centimeter into 100 centimeters, It will be 1 into 10 raised to 4 or 10,000 centimeters square per second or 10 raised to 4 centimeters square per second, or we can say it is 10 raised to 4 stokes. So you can just see here 1 meter square per second will be 10,000 stoke. Okay. Again here also 1/100th of a stoke is named as centistoke. It's not written here, but one can take that 1 centi, that is C stoke, 1 centistoke is equal to similarly 1/100th of 1/100 of stoke, lowercase letter s, so that it is a unit of measurement, not the person's name. So that is it. 1 centistoke will be equal to 1/100th of stoke. Okay. Next, we'll try to analyze a couple of situations. You can do it easily. If the fluid has a dynamic viscosity of 1.5 pascal second and a density of 0.8 grams per cc, so this is density rho, this is mu, then we can say that it has a kinematic viscosity of. Now, how to calculate kinematic viscosity? We know the relation. Kinematic viscosity is nu, and this nu is equal to, we know that it is a ratio of mu to rho. Only thing is we have to properly substitute the units. Here it is 1.5 pascals or 1.5 Newton second per meter square, and density is given as 0.8 grams per cc. You have to convert this into kc per meter cube, so that exercise you have to do, and not kg per meter cube, you can convert it to centimeter also. So by adjusting the units you should come out with what is the value of viscosity, kinematic viscosity in centimeter square per second. So this you can try on your own. Now take for the fluid second situation, mu is equal to 0.1 pascal second. From stationary surface plate, if the velocity is 5 meter per second at a distance of 5 millimeter, then the shear stress is, try to understand, here there is a stationary plate at the bottom, okay, and there is a moving plate on the top. So if I am able to explain this way, then the same viscosity of the fluid is given, and from the stationary surface plate, if the velocity is 5 meter per second at a distance of 5 mm, means this distance is given as 5 millimeter, means whatever we have discussed as t, that t is 5 millimeter, and the velocity over here is 5 meter per second. So this v is 5 meter per second. Now we should apply Newton's law of viscosity and then try to find out the magnitude of whatever required things are there. Now, equation to be used is tau is equal to mu into du by dy. So this equation has to be used for analyzing this problem. You give a try. Let us discuss these problems in the coming videos. Okay, here viscosity of variety of liquids is being discussed. So this I'll discuss in the next video. Thank you. We'll stop here.